As we come to class on Thursday or Friday, depending upon your day, we will be shifting momentarily to a focus on probability. Okay. As you know, our course is entitled Elementary Probability and Statistics. So, for the most part, all of the concepts that we cover will be from a very basic understanding, an introduction to these concepts. However, when we start working with probability, even though we are working at an introductory place for college or advanced high school students, there are some general foundational skills and pieces of knowledge about probability that it's sort of assumed that you come into the class with from maybe your middle school days or your early pre algebra days, somewhere along those lines. So, the purpose of part one here is to walk you through some of those basic skills that you may have done at one time, forgotten, or maybe perhaps don't ever recall seeing. So, this is kind of just a review of those things that you're going to need to know coming into the practice that we're going to do in class when you come to class on Thursday or Friday, depending upon your group. Okay, so, our introduction to probability here relies on us visualizing most of the events that we are looking at as a random process. Okay, so what does it mean to be a random process? A random process is an experiment. Okay, we're going to do something and see what happens. And in this experiment, we cannot predict the outcome in advance. But there is some sort of pattern we expect to see long term. So, in other words, if we were to repeat this experiment over and over and over and over again, forever and ever and ever, there would be a particular pattern among those results in the long term. What are some examples of those kinds of things? Flipping a coin and recording the result. Okay. For example, we know the probability of getting heads would be 1 out of 2. One success out of 2 possibilities. Okay. We know that's a 50% probability, okay, or a 0.50 probability if we express that as a decimal. Now, we know if we flipped 10 coins, we're not guaranteed to get 5 of heads and 5 of tails because it is possible that we would not get a 50-50 split exactly. It is possible that we could get a 50-50 split exactly. But we know that if we flip this coin a million times or an infinite number of times, even if we exceeded a million, we would see a pattern that shows us about half of those flips turned out to be heads and about half of those turned out to be tails. Okay? That can be expanded upon. Instead of flipping a single coin and counting one result, we also could flip multiple coins. So imagine flipping 3 at a time. Okay? And recording the number of heads that we see, or flipping 3 in a group consecutively would yield the same situation. Okay. Rolling a pair of dice and recording the sum or adding the dice, that would also be an example of a random process. Picking a person at random from the classroom and then measuring their height in inches. Okay. Now, when we think of these random processes, we also start to think about the sample space, or we should think about the sample space. Now, what is that? The sample space for a random process is the set of all of its possible outcomes. So, if you think about flipping that individual coin, that was the first example. The sample space is heads or tails, okay? Because that is the result that we can get. We're recording whether or not we get heads or tails. Now, I want you to look at the second one and focus on it a little bit clearer. if we flipped three coins and then recorded the number of heads. So we would not be recording the individual outcome for each coin. However, how many out of those three had heads as their outcome? If we recorded that, the possibility is 0, no heads, only 1 landed on heads, 2 landed on heads, or 3, all 3 landed on heads. For example 3, the sample space is 2 through 12. That is because if we're adding the number value of each dice face, the lowest combination we could make is 1 plus 1, which would be 2. And the highest combination we could make would be 6 plus 6, which would be 12. For sample number 4, example number 4, the sample space for that is pretty much any numbers between about 54 inches and about 80. Although it is possible we get measurements outside of that range, typically this would be a sample space that would take care of heights of a random person. Okay, so we'll look at some alternate ways to describe the sample space for scenarios 2 and 3. And that was flipping the 3 coins and recording heads. And this was rolling the 2 dice and recording their sum. Okay, now a little bit more terminology here. An event is a subset of the sample space. Okay, so in one possible event is A, the result equals heads. So if we were to perform that process one time, that of course is our event. Okay, so in example 2, 2 possible events are exactly 2 heads and no more than 1 head was flipped. In example 3, 2 possible events are a sum of 4 was rolled and E, a sum of 6 or less was rolled. Notice that these descriptors include more than one possibility. If we say no more than 1 head was flipped, then that means it could have had 0 heads or 1 head. We could not have had 2 or 3 in that result. In example 4, one possible event is the person selected was at least 70 inches tall. At least means 70 or greater. Okay. We can often describe events by listing all of the possible outcomes in an event. Okay. So if we did this, we have included the same events described on the previous slide inside brackets or braces here in terms of possibilities. Notice that if we're not rounding to the nearest inch, we would use interval notation to represent the range of values between here. Okay. Another way to consider outcomes is when we have a random process repeated. That's similar to our example of flipping a coin 3 times in a row, or rolling a pair of dice and adding the results. It's often useful to think of outcomes as a list of the results of individual performances of the process. Okay? For instance, there are 8 different lists of individual outcomes that can result from flipping a coin 3 times. If you have never had to think about all of the possible outcomes of a multi-step event, then I would strongly suggest that you reflect back on your days in middle school and perhaps think about drawing a tree that might help you with that. Okay, for example, let me just bring up a blank document here in Word. If I think about flipping 3 coins, okay, I'm going to get 3 individual results of heads or tails. If I flip them all at the same time, or I flip them in groups of 3, then I'm going to count the number of heads or the number of tails as I have described in my scenario. Okay, so let's show how we could keep track of all of the possible combinations here. If we think of flip 1, okay, that coin 1 is going to be flipped, and we know no matter what, that's going to result in a heads or a tail. Now, when we go to flip coin 2, it also will result in heads or a tail, but it would produce a different combination depending upon what we got when we flipped the first coin. So how can we illustrate that? If we got heads on the first coin, and then we had the option or heads or tails in the second coin, we have produced two different outcomes here. Heads, heads, heads on the first, heads on the second, and heads, tails, heads on the first, tails on the second. We can do the same thing with tails. Okay? And as you might have guessed, you can continue that pattern to accommodate for the third coin being flipped. Okay? Now, we make this a tree because it kind of starts to branch out. This is an example of making like a vertical tree, but I've also seen people draw these horizontally. But one thing to remember is that each branch at the end of this tree is going to represent a different possible outcome for the process that we've shown. How does it do that? Track the end branch all the way back to the beginning. So if we follow this most outside branch here, we would go heads on the third, heads on the second, heads on the first. So the outcome here, heads, heads, heads. Similarly, I would start here with the tails, tails, heads, 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 tails, heads, tails, tails, heads, 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 tails, heads, tails, heads, tails, and heads, tails, tails, and finally tails, tails, tails. So out of flipping those 3 coins, we have a total of 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes in our sample space there. Any of those 8 could be the specific result of one action in this random process that I am partaking in. Okay? So this is what we're looking at here when we see this list of possible outcomes. If we were to distinguish between the 2 die being rolled in that example, say one of them is red and one of them is green, then we get 36 unique different results. Okay, saying we list the red roll first. Some of them might be red 1 and a green 1, red 3 and a green 4, red 2 and a green 5, and so forth. Okay, doing this will be vital for dealing with upcoming probability computations. So if you're struggling to see the sample space, and obviously many students do, especially when we add more actions or more events in a particular random process, or we add more possible outcomes for each event. Every time we do that, we're making it a little bit more complicated to track down all of the possibilities. I strongly suggest that you use a probability tree in order to help you do that if that's something that you've struggled with in the past, or draw and make charts. Those are also additional ways to visualize that. Okay, so in this alternate way to think about outcomes, the event B from a couple of slides ago, okay, is now heads, heads, tails, heads, tails, heads, tails, heads, heads, and event C is tails, 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 heads, tails, heads, tails, and heads, tails, tails. Okay, so let's go back and look at that again to make sure that you see that. If we look at B, exactly 2 heads were flipped. And then we come over here and we think about how could that happen? Exactly 2 heads. These are all of the outcomes that produced exactly 2 heads in my 3 coins being flipped. If we look at C, Okay, put this here. No more than one head was flipped. These are the outcomes that have no more than one head. So 0 heads, 1 head, 1 head, 1 head. Okay. Event D, okay, event D is a sum of 4 was rolled. So if we were thinking about that in terms of our dice, these are all of the possible ways that we could make 4, assuming we have unique die. Okay, this might be a red 1 and a green 3, whereas this might be a red 3 and a green 1. Those would be a unique particular outcome in that description. What about event E? Okay, E, if you go back, was a sum of 6 or less. Okay, if that's the case, we could break down each possibility of ways that we could make 6 or less. Okay, let's think about that. We could start with 1 and 5. That would be a possibility. Also, 2 and 4. 3 and 3. Now remember, we are assuming we have 2 different colored dice, and the first one is red. Since that is the case, that result of 3, 3 would be a red 3 and a green 3. We would not need to list that again because no matter what happens here, okay, we have rolled a 3 on both of those die. We also could have, though, created a 4, 2 roll, red 4, green 2, instead of the opposite, and a 5, 1. So 1, 2, 3, 4, 5 rolls, 5 different ways out of 36 combinations that we could roll a sum of 6. Pretty sure it just says, 6 or less. Okay, so I have not accounted for the or less. That would be the sum of 6. So what would be less than 6? We would also look at the ways you could make 5. We would also have to consider the ways you could make 4, 3, and 2. All of those would have to be considered as successes in this case. So as we said, we had 5 possible ways to make 6. If we look at creating 5, we could roll 1 and 4, 2 and 3, 4 and 1, okay, or also 3 and 2. So we have 1, 2, 3, 4 ways that I could make 5. What about rolling a combination of die that would produce 4? We could roll 1 and 3. We could roll 2 and 2. We also could roll 3 and 1. So 3 possible ways to make a 4. Making a sum of 3, 1 and 2. Okay, that would be an option. And also 2 and 1. So 2 possible ways to make a 3. When it comes to the 2, the only way possible to do that is to roll a 1 and a 1 on both die, which produces 1 way. When you combine all of the possibilities of getting a 6, a 5, this is 9, plus 3 more to make the 4 would be 12, plus 2 more is 14, plus 1, we would be looking at 15 out of 36 as the possibility or the probability that we would roll a 6 or less when it comes to rolling 2 die and adding them up. Okay? Now, when we think about probability, in this class, probability will most often be expressed as a decimal, a value between 0 and 1 that measures the relative likelihood of that event. Obviously, the closer we get to 1, the more likely an event is to happen. An event with a probability of 0 never ever happens. It's an impossibility. An event with a probability of 1 is a 100% certain chance that this will occur. In our first examples, there are a relatively small number of outcomes in the sample space. Okay? And furthermore, we're assuming every outcome is equally likely to occur. Think about what we're doing with the coin flip and dice rolling outcomes on the previous two slides. We're trying to view the outcomes in such a way that they're all equally likely. Okay. So when we think of probabilities with equally likely outcomes, we can describe probability as the number of outcomes in an event. Okay, so the probability of something happening in an event, that number of outcomes, that the ways that could happen, over the number of outcomes in the entire sample space. Okay, so the number of ways the outcome we're studying can occur, that's our numerator, over all of the possible outcomes that could ever happen in the sample space. Most of us are thinking about our basic probability in middle school, where we thought about successes out of the total possible ways something could occur. In statistics, you'll often see probability referred to using the capital letter P. Okay? You will also see those subsets of parentheses. Right now it has the word event in it. This would be read as the probability of the event occurring. You can replace the word event with whatever specific outcome it is that you're trying to calculate the probability of. Okay. As we saw a few slides ago, there's 4 ways that I can get 0 or 1 heads and 3 flips. While drawing out our outcomes, we see 0 or 1, that's 1 or less. Okay? So no heads, 1 head, 1 head, 1 head. There are 8 possible outcomes altogether. These 4 we just listed, plus the other 4 where there is more than 1 head. 2 heads, 2 heads, 2 heads, and 3. So the probability of getting at most 1 head in 3 flips of a coin is 4 out of 8. 4 of these 8 possible outcomes would give me a success if I were trying to produce the event of getting 0 or 1 heads. 4 out of the 8 total make that a success. So the probability of getting 0 or 1, or at most 1 head, is 1/2. There are 5 ways to roll a sum of 8 on 2 dice, and we can easily tell these apart, especially if we've color-coded them. So there are 36 different possible combinations in all of the die. If you think about, you're not quite sure how that value is calculated, think about the number of selections that you have for each of the die. We can get anywhere from 1 through 6 on the first die, and then no matter what we get on the first, we can get anywhere from 1 through 6 on the second. So we will make 36 combinations. We will make 6 individual unique combinations for every possible value that can be rolled on the first die. Since there's 6 of them, that yields 6 times 6, which is 36 possibilities. If we're looking for the probability of rolling an 8, which is what this demonstrates here, then we had 5 unique outcomes, which could make that happen as a success out of 36 of the total possible outcomes. Okay? If there are 4 ways of rolling a 9, a 3 and a 6, a 4 and a 5, a 5 and a 4 and a 6 and a 3, then the probability of rolling a 9 would be those 4 out of the total of 36 outcomes that we're looking at here. Okay? Now this is where we have to do a little bit of thinking. We often refer to different kinds of events in this class and in our work with probability. We talk often about mutually exclusive events, and we call these sometimes disjoint. It pretty much means they share no common outcomes and could not happen simultaneously or at the same time. For example, the events getting exactly 1 head in flipping 3 coins and the event of getting exactly 2 heads are mutually exclusive, which means we could not flip 3 coins and at the same time get exactly 1 head in that combination total, and also get exactly 2 heads total in that combination. It's going to be one or the other. Okay? The events rolling an 8 And rolling a 9, we mean sum here, sum of 8, sum of 9, and throwing 2 dice are mutually exclusive. The events rolling an 8 and rolling an even number in throwing 2 dice are not mutually exclusive, okay, because you can both be an 8 and an even number. There's overlap there, okay? So how do we deal with mutually exclusive events? If we have two events, we'll call them A or B, okay, and we want to know the probability, okay, that either A or B or both, okay, if we're looking for some combination of that, when they're mutually exclusive, if I want to know A or B, I'm willing to accept either one of these, then I can add the individual probabilities together. Imagine a bag that has 3 marbles in it. One is red, one is blue, and one is green. If I think about the probability of getting any specific color, it's just 1/3. One possible marble out of the whole 3 will be a success for any given color. But what if I change my willingness to accept 2 different colors? If I say I'm going to reach into the bag and I'm going to pull out 1 marble, what is the probability it will be red or blue? Now there's 2 possible ways I could be successful in this circumstance. I have 1/3 of a probability for red plus 1/3 of the probability for blue, which equals 2/3 of a possibility of getting a success. We add those individuals. So as you see here, this details more examples referring back to the previous context we've used of how we would consider adding the probabilities of mutually exclusive events to consider the probability of either of those occurring. Okay. This also brings us to an interesting concept called the complement of an event. It's the set of outcomes that are not in the event. Okay? The complement of rolling a 6 or less is rolling a 7 or higher. So pretty much after all of our successes have been taken out or considered, the complement would be everything that is left. The complement of flipping exactly 2 heads would be flipping 0, 1, or 3. Basically anything with the exception of what we have already defined. We call a complement a to the power of c. You would notate this quite often. So if I've listed an event and have a little superscript of c, we're talking about the complement of whatever that event is that is described as event A. Okay? So think about this. If we know the probability of any event, and we want to know the probability of its complement, all we should have to do is subtract that from 1. Okay? How does that make sense? Let's stop for a second and think about the marble and the bag scenario I discussed earlier. It was very simple. If I said I'm willing to take a green or a blue, we had 2/3 of a possibility or probability of getting that accurate marble that we're looking for the probability of here. What if we were asked for the complement? What would the probability be of getting a marble that is not green or blue? Okay, it has to be what is left. And since the probability of the event was 2/3, the probability of the complement must be the other 1/3 that we are considering here. Together, an event's probability and its complement added together should be 1, because we do know for certain that one of the 2 things will happen. Either we will get something that meets our desired event that we're considering the probability of, or we won't. We'll get anything else that doesn't fit in that. So when you think about I will see the event I'm looking for, or I won't, those 2 options combine for a certain 100% guarantee that one of those will occur. Okay? So what about independent events? We've already discussed when we're willing to accept either or option as a success. Independent events, we're dealing with these when we have the knowledge that one of these things occurring does not affect the probability of the other. Imagine flipping, this is kind of like a compound event. We're flipping a coin and we're rolling a die. So flipping the coin would not have any effect on rolling the die. Okay, it's not going to change the outcome. In this case, these are independent events. Knowing the result of the coin flip in no way impacts what will happen when we roll the dice. Okay, so let's say we have two additional events here, C and D. C is we roll a pair of dice that adds up to 9, and D, one of the dice is a 6. If our pair of dice actually does add up to 9, there are only so many combinations that we can use that would add up to be 9, and that would limit how many 6s were available to us. Okay, so this probability, this occurrence of this event, affects what we have or changes our probability here for the second event. They're not independent. Okay, we just discussed that. Okay. Now, how can we use calculations with the idea of independent events? If we are dealing with independent events, most of the time we are looking at the probability of having two things simultaneously occur. We don't want either or, we want both. Okay, so when these events are independent, we can find that probability of both occurring by multiplying their individual probabilities. This also extends to not just two, but three or more independent events. No matter how many times I wanted to flip that coin or roll that die, I could continue to look at individual results and multiply the probabilities of those results. Here are additional examples. If I want to flip a coin and roll a die, and I want to know the probability of getting heads and rolling a 6, I want both things to happen. I want to flip the coin and roll the die, and I want the coin to say heads, and I want the die to say 6. I take the probability of heads, 1/2, the probability of getting a 6, 1/6, and I multiply them. So the probability of getting that combination is 1/12. Okay. A on the first flip, we're flipping three coins here. Getting heads on the first flip, heads on the second, and heads on the third. So this is the probability of flipping those three coins that we've been discussing and getting heads, heads, heads. Okay, heads on the first, heads on the second, heads on the third. 1/2 plus or times 1/2 times 1/2. So 1/8. We computed the probability of flipping heads 3 times in a row in a different way earlier. If you remember looking at the different possible outcomes when we wrote that sample space down, these were the 8 outcomes. You see these? How many of them produced 3 heads? Only 1 out of the total 8. So we've calculated that in a different way earlier. So this is the end of sort of the basic ideas of probability. If this is something you're familiar with, then you should be able to come to class and do very well on Thursday and Friday in the practice questions that we'll be doing. If you're not going to be in class on Thursday or Friday, then you do want to go ahead and watch part 2. If you're in class on Thursday or Friday and you find yourself a little bit confused, it wouldn't hurt maybe to also view part 2 and maybe go to the parts you were extra confused on and re-listen to that information, or be able to pause it, rewind it, and so forth. If you have any additional questions, please let me know.